Chapter 5 covers isomerism. Isomerism can be broken up into two different categories. One of them is constitutional isomers that have different constitutions, meaning that the covalent bond connectivity is different. And the second is stereoisomers, the main focus on this chapter. And these are different, but the 3D bonds connecting them are the same. Before we talk about isomers, let's talk about chirality. Chirality of an object is when you have a mirror image, but that mirror image isn't the same as itself. For example, if you think about your two ears, your ears are quite similar, but when you consider the symmetry between them, they're related by a mirror, which can be used by this symbol sigma that's used to show that there's a mirror. Your hands, likewise, are not the same. They are non-superimposable. Hands are non-superimposable mirror images. Molecules can also be non-superimposable mirror images, and I've shown an example here. You can see that if you trace everything from the left to the right, it all matches. But if you try to make a model of this compound, you won't be able to overlay these two molecules. If this is not something you can see, you must build these two molecules yourselves and convince yourself that this is not the same molecule. It's not reoriented differently. They are simply two different molecules. Again, they are mirror images of each other. A chirality center discusses tetrahedral carbon atoms that are bearing 4 different substituents. For example, in the first molecule, we have a hydrogen atom that's not shown for a total of 1, 2, 3, 4 different groups around the bromine atom, or around the carbon containing the bromine atom. It does not matter that there's a carbon here and a carbon here. What matters is that there's an ethyl group and a methyl group, and those are not the same. Similarly, this sulfide compound has an implied hydrogen atom, giving it 1, 2, 3, 4 unique groups. So this is also a chiral center. If we proceed to the next compound, we have again an implied hydrogen atom for a total of 1, 2, 3, 4. Again, it doesn't matter that we're going around this ring. That ring is not a symmetrical ring because it has a double bond. In the last example, I've drawn this molecule with a wedge, and we can put an implied hydrogen behind it. But when we look for chiral centers, notice that we've got one ring going around the molecule, and then the other half of the ring going around the molecule. And these are the same. This molecule is symmetric, so this is not a chiral molecule. Types of stereoisomers range from mirror images to not mirror images, where the mirror images are enantiomers and the not mirror images are diastereomers. So let's consider these classes of examples and go through whether they are mirror images or not. At first, the molecules may not look like mirror images, but you have to consider all rotations of these molecules. So let's rotate that second molecule and see if it looks more like the first. Just rotating it in the plane of the page. And now what I hope you can see is that between these two molecules, there is a mirror. So these are enantiomers. Again, if any of these are a struggle to you, just get out your molecular model kit. They're highly underutilized in this class. In the second set of molecules, it's again not obvious what's going on, so we need to rotate the molecule either with a physical model or through space to see what's going on and flip those substituents. And what do you see here? What is the relationship between these two molecules? In fact, these are the same molecules, so they are not a stereoisomer. In the third set, let's rotate that second molecule. And here what you can see is that the bromine has a wedge in one case and a dash in another case. So these are also, these are diastereomers because they are stereoisomers that don't have mirror images. The case for cycloalkanes has been a little bit harder. What I like to do with cycloalkanes is make them into a flat form as far as the representation goes and ask where the atoms are going with wedges and dashes. Because it's often easier to move these around in your mind. Oh, notice that I've got a small mistake here. There. This one should be an OH fixed. Okay. And for the bromine one, I'm going to give that a down for the bromine that's on this carbon. And then going 2 carbons over, then we see that this oxygen group having a down hydrogen is on an up. Now that we've got the molecules like this, it's more obvious to see that these are enantiomers of each other. Enantiomers have the same physical properties as one another, but they interact with rotated plane polarized light differently. That you can't separate them by conventional means because of their same physical properties. Diastereomers have different groups of compounds arranged in different ways, so they are going to have different physical properties, and they often can be separated through crystallization, chromatography, a variety of methods. Meso compounds are an interesting class of molecules because they have chiral centers, but they themselves are not chiral. If you look at this compound, it definitely has 2 chiral centers, but what it also has is a plane of mirror symmetry that dissects the molecule in half. This would be like your nose. If you have a nose, talk about an ugly looking nose, then this nose has a plane of symmetry down the center of it. So your nose, unless it's grossly misshapen, is a meso well, your nose is meso, assuming it's symmetrical left to right. When you have a meso compound, these don't interact with plane polarized light, and they do have stereoisomers, but they themselves are not stereoisomers. Let's consider dichloroethane. Is dichloroethane a meso compound? Well, when you look at it this way, you can't see the mirror image that goes down through it. But if you rotate it across that bond, that C2C3 bond, now you can see that there is a mirror plane of symmetry from left to right. And again, this is another meso compound. So everything here is meso. There are also compounds exist that are chiral compounds without a tetrahedral carbon atom. For example, this BINAP derivative is locked in a conformation that keeps it from being a free rotating molecule. So it cannot rotate around that carbon-carbon bond, which means it's stuck in this conformation. BINAP has an R and an S conformation, so because it's locked in that conformation, it is chiral, even though we're not giving it a chiral tetrahedral carbon atom. Another compound that is chiral are the trans and cis versions of alkenes. These don't have tetrahedral carbon centers, but they're definitely of the same composition, and they're not the same as each other, so they have to be stereoisomers, and in fact, they're diastereomers. Lastly, we have the compound set called an aldene. And if you recall about the molecular orbital theory for something like this, we have a pi bond on the left. Let's make these vertical pi bonds. And then you have a pi bond on the right. And this pi bond cannot overlap. It's not going to be the same as the pi bond that already exists. That's impossible. So we're going to rotate this pi bond 90 degrees to the right, which means that the pi bond on this carbon is also rotated 90 degrees to the right. And then we're looking for where can we put our substituents that remain, and these are going to remain in sp2 hybridized orbitals. So we've got our p orbitals, and then the remainder are sp2 except for the hydrogens, which are sp3. I encourage you to build a model of the system so it's obvious that these are not interchangeable. We've basically got 2 blocks of wood that have different things coming off of them, and if you change the placement of 2 of them, then you're going to have a stereoisomer. That's all for chapter 5. What did I do?